Colligative properties of solutions. Colligative properties depend only on the number of solute particles and not their identity. So it doesn't matter what the solute is. There are three colligative properties: vapor pressure lowering, freezing point depression, boiling point elevation. Vapor pressure lowering first. Vapor pressure is the pressure exerted by a vapor in equilibrium with its liquid. I like to think of vapor pressure as this. As a liquid evaporates, the vapor has a pressure, and I like to think of vapor pressure as the pressure that pushes upward from a liquid as the liquid evaporates. When you add a non-volatile solute, that is a solute that does not evaporate, into solution, the vapor pressure of the solution is lower than that of the pure solvent. So why is vapor pressure lowered? Well, water molecules surround the ions that are dispersed throughout the liquid. So let's say I have sodium chloride as my solute. Water is my solvent. Well, water surrounds these ions. Water is polar, slightly negative, slightly positive, because of the lone pairs on the oxygen. And so some of the water molecules are surrounding the ions. You also have chloride ions down here, and the water is doing the same thing. It's surrounding those ions. Well, because water molecules are solvating the ions, less water molecules have enough kinetic energy to escape as a vapor, and so the vapor pressure of the solution gets lowered. Ionic solutes, that is, solutes that have a metal and a nonmetal, dissociate to have greater effects on the vapor pressure than a non-dissociating solute. For example, sodium chloride produces two particles in solution. When you put sodium chloride in water, it produces Na plus and Cl minus. So there's your two particles. Magnesium chloride produces three particles, one magnesium ion and two chloride ions. There's your three particles for MgCl2. Chromium nitrate, you'd have one chromium ion plus 3 charge. You would have 3 nitrate ions for a total of 4 particles in solution. So if I have the same amounts of each one of these solutes, chromium nitrate would have a larger effect on vapor pressure. The vapor pressure would be lowered more with the chromium nitrate because it produces 4 particles in solution. Freezing point depression is the second colligative property. The freezing point of a solution is lower than that of the pure solvent. And the reason this happens is if I add a solute, again we'll use sodium, and dissolved in water, well, the sodium disrupts the orderly freezing pattern of the water. In order for water to freeze, the water molecules have to touch one another. If these ions get in the way, it disrupts that orderly freezing pattern. And so more kinetic energy must be withdrawn from the solution in order for the water to solidify, in order for it to freeze. Freezing point depression is the difference in temperature between the freezing point of the solution and the freezing point of the pure solvent. If we're looking at water, water freezes at 0. Water freezes at 0 if it's just pure water. If I add something to water, the freezing point will decrease below 0 degrees Celsius. Now, the magnitude of the freezing point depression is proportional to the number of particles because it's a colligative property. It does not depend on the identity of the solute particles. Let's look at a couple examples. 1 mole of glucose lowers the freezing point to negative 1.86 instead of 0. But if I add 1 mole of sodium chloride, the freezing point gets lowered to negative 3.72 instead of 0. Well, why the difference? Glucose contains all nonmetals. It's a non-dissociating solute. Sodium chloride contains a metal, so it produces 2 particles in solution, Na plus and Cl minus. So why the difference? Ionic solutes have greater effect on all colligative properties. In this case, freezing point depression. So ionic solutes have a greater effect. They will lower the freezing point more than a molecular solute. Third colligative property is boiling point elevation. Boiling point is the temperature at which the vapor pressure equals the atmospheric pressure. So a solution will boil when the vapor pressure, the pressure pushing upward, equals the atmospheric pressure, which is the pressure pushing downward. That's when a solution will boil. Well, when I add a non-volatile solute, a solute that does not evaporate, it decreases the vapor pressure, so additional kinetic energy must be added to raise the vapor pressure. So consequently, the boiling point is higher than that of the pure solvent. Boiling point elevation is the difference in temperature between the boiling point of a solution and the boiling point of the pure solvent. Now, if we're looking at water, water normally boils at 100 degrees Celsius. If I add something to water, the boiling point will increase, and the magnitude will be proportional to the number of solute particles dissolved in the solvent.